You're listening to the Thesis Review podcast. I'm your host, Sean Wellick. I'm a PhD student at New York University, and my research focuses on machine learning, natural language processing, and structured prediction. On the Thesis Review, I'll interview researchers from around the field, centering the conversation around their PhD thesis. In addition to exploring the technical content, this will give insight into their history as a researcher, allow us to revisit older ideas, and provide a valuable perspective on how their research and the field itself has evolved since their PhD days. My guest today is Chelsea Finn, who is currently an assistant professor at Stanford University, where she leads the IRIS lab that studies intelligence through robotic interaction at scale. Her research focuses on the capability of robots and other agents to develop broadly intelligent behavior through learning and interaction. Her work has included deep learning algorithms for concurrently learning visual perception and control in robotic manipulation skills, inverse reinforcement learning methods, and meta-learning algorithms that can enable fast, few-shot adaptation. Her PhD thesis is titled Learning to Learn with Gradients, which she completed in 2018 at UC Berkeley. She received the ACM Doctoral Dissertation Award, a prestigious honor awarded to the author of the best doctoral dissertation in computer science and engineering, so I highly recommend reading it, and it was a great honor to talk with her today. We discussed machine learning for robotics, focusing on learning to learn, or meta-learning, and her work on the MAML algorithm during her PhD. We talk about how she used MAML for teaching robots to rapidly learn a new task by only watching a single video of a human demonstrating the task, or for inferring goals. Finally, we talk about the many exciting challenges that remain and where she sees the field going next. The Thesis Review is available on SoundCloud, Apple Podcasts, Google Podcasts, and Spotify. And be sure to follow us on Twitter at Thesis Review. If you would like to support the podcast, you can contribute $1 at buymeacoffee.com/thesisreview. There are links to Chelsea's thesis, the papers that we mentioned, and her ongoing course on meta-learning in the show notes. Here's Chelsea Finn with Learning to Learn with Gradients on the Thesis Review. So your thesis discusses learning to learn, and I thought before we talk about that, we could ask a kind of maybe ridiculous question, which is, do humans actually do things like learning to learn, or 4 levels deep, like learning to learning to learning to learn? And is it enough to just study learning to learn, or do you think we'll have to go and study 1 level deeper someday?
Yeah, I think that it's possible that we may want to go deeper. Well, with the caveat that I'm very much not a cognitive scientist or a neuroscientist, and I don't study human behavior. It does seem like humans do some forms of meta-learning. We're able to kind of acquire new skills and pick up new skills more quickly as we get more experience with learning and organizing thoughts in our mind. And I think that if you take in kind of evolution into play as another learning process over time, it does seem like there are probably more than just, it is probably deeper than meta-learning in the sense that evolution might be the highest level process, and then humans ourselves may also be doing a form of meta-learning. So kind of taken together, that may be a form of meta-learning. From a more practical standpoint, so from that standpoint, it certainly could make sense. It does seem like there's some form of meta-learning going on. From a practical standpoint, I'm not sure if we're ready for that right now. I think that the algorithms that we have currently typically require, so I guess we'll get into some details later, but they require distributions of tasks, or essentially data sets of data sets. And constructing individual data sets can already be a bit of a burden for people. And so constructing a data set of a data set is a bit burdensome as well. And so then if we go 1 level higher, we need data sets of data sets of data sets. And that makes it like even harder to consider what we would do for these, how we would actually provide that to these algorithms. So I think that we need more development on thinking about how we feed in data to these algorithms before that really becomes practical. Mm-hmm. I also like thinking about it more, not necessarily as going deeper, but thinking about learning on different timescales. we want to be able to learn on very quick timescales, on medium timescales, on very long timescales, on potentially evolutionary timescales. And that doesn't necessarily need to mean that we're going deeper in the hierarchy. That may mean that we just need to be learning at all possible levels of time.
So yeah, you've noticed maybe a ridiculous question. It seems like maybe if you had some open-ended world, like maybe the world we live in, then maybe there are these multiple like levels of learning going on, and the world itself is kind of generating the requisite tasks to do it.
Yeah, I think that if we can think of if we can like ultimately put agents in the real world, then that and they have means to construct tasks themselves, or the world is somehow making it clear to them what they need to do, then that may make these algorithms more practical, and in general, it makes machine learning more practical as well. And as the complexity of that world increases, also I think the complexity of the behavior that's learned will also have the potential to increase. It actually kind of bugs me a lot when we run a lot of experiments on really simple worlds, because the only thing that you'll be able to get out of very, very simple worlds is very simple behaviors.
Hmm. Yeah, I see. So maybe let's go to before your PhD. So how did you initially get interested in artificial intelligence and robotics?
Yeah, I think that I've actually always been interested to some degree. I did a little bit of Lego robotics as a middle schooler, where we built robots out of Legos and programmed them and competed. There was actually a 2.5 minute time limit to complete a number of tasks with your Lego robot, which was pretty cool. I actually wasn't really sold on robots at that point. I also really like topics in biology. I think that the way that the human body works is amazing. Uh, coming up from just all these, we basically have these cells, and the human body is made up of all these cells, and the way that they all come together to create what we are, I think, is incredible. And was when I started college, I was thinking about doing something in bio, considering doing something in computer science. I ended up moving towards computer science because I really liked that it opened many doors. It gave you the tools to do many different things, and it would allow me the opportunity to potentially go into like computational bio if I wanted to just kind of stay in that region, or go in other paths like robotics. And then from there, when I started a computer science degree at MIT for my undergrad, um, the classes on computer vision, machine learning, and AI were always the most fascinating to me. I actually took a graduate level computer vision course my sophomore year of college, which was maybe a bit too early to be taking a class at that level. Um, and was always kind of fascinated by the topics. And I also, I guess, in general, I'm fascinated by how, like, what intelligence is and how we might recreate it. I've also been really excited about the potential positive implications from this technology on society, especially in the form of robotics. There's medical robot applications. There are kind of disaster relief applications, and other kind of public service applications that you can imagine if we had capable robots that could help and operate intelligently in everyday environments.
So I guess it was a mix of like the technical interest, but then also looking kind of ahead to like how you could apply this to practical problems.
Yeah, absolutely. And I actually, back in 2010, I wrote my one of my college admissions essays. Actually, maybe back in 2009. One of the schools I was applying to was Cornell, and they required you to write about some technology that you wanted to build. And I actually wrote about self-driving cars and trying
Mhm.
to minimize the number of accidents, because I was actually in an accident, was hit by a distracted driver when I was
Oh, cool.
16, and was kind of heavily motivated by that to try to um, build autonomous cars that don't have the distraction that humans have. And that was kind of back before driverless cars were the kind of thing that they are today.
And then at what point did you decide to do a PhD or to focus on research?
Yeah, I this wasn't really the path that I was planning on going. My both my parents are engineers and worked in industry for a long time, and that was kind of the way that I thought that you can have impact with the work that you do. But I soon realized that if you wanted to work on topics in AI and robotics and machine learning and really be at the forefront of those techniques, you really need to be in research, at least as of 2014, because In industry, it really just kind of amounts to taking a model and trying to apply it to a certain problem. Whereas if you want to actually develop new algorithms and develop new techniques for robots or other things, yeah, I found that all the people doing that in industry all had PhDs. So I was like, well, maybe I should get a PhD too, so I can do those cool things as well. Um, it's always Research has always been quite appealing to me because it basically amounts to trying to solve puzzles and try to solve problems that no one has figured out how to solve yet.
And then when you got to Berkeley, did you know kind of what you wanted to focus on, or at what point did you start to focus on robotics and then ultimately just meta learning?
Yeah, so applying to grad school, I knew that I wanted to do something in AI. I wasn't really sure of the application area, and I was actually still considering computational biology and kind of bio applications of AI at one point. But through visit days, I kind of figured out that robotics it seemed like a good thing to be working on. It seemed like something that would be quite relevant by the time I was graduating still. It seemed like a very challenging problem. Um, and so when I got to Berkeley, I had primarily talked to Peter Abiel and Trevor Darrow, who does a bit more computer vision at Berkeley, and started working with them when I arrived. Knew I wanted to work on kind of robotics problems right from the start, and thinking about applying machine learning techniques to robotics.
So if you could think back, like where was the field at that time? Was deep learning being applied to robotics yet, or?
Yeah, so my senior spring at MIT, actually, in this was spring of 2014. I took a second computer vision class with Antonio Torralba, who's a well-known computer vision researcher, and he actually didn't cover neural networks at all in that class. And this was like kind of around the time and slightly after some of the kind of revolutionary advances with convolutional neural networks for computer vision. But when I came to Berkeley, it was a completely different story. Deep learning was kind of really up and coming at Berkeley. At MIT, it was, I think, took a little bit slower for people to accept it and adopt it. Especially this is all kind of in computer vision, and in robotics, there was very little work around that time that was looking at neural networks and deep learning for robotics. But it was a kind of a great place to be studying that because a lot of the computer vision researchers were quite excited about neural networks and deep learning.
So it was mostly like classical control still, like for the problems you were maybe initially working on during the PhD.
So it wasn't classical control that I was working on. The So Peter Abiel's lab at Berkeley at the time was using machine learning for robotics. They just weren't yet using deep learning, and Peter's lab was also one of the only labs doing any form of machine learning for robotics. I remember going to a conference, I think my first or second year, and there was like 2 sessions on machine learning for robotics on what's called learning and adaptive systems, and like half of the papers in that session was from Peter's lab. Uh, and so there were basically so few people that were working on any form of machine learning for robotics. They were more working on kind of classical control techniques for controlling systems and other kind of classical perception techniques as well.
I see. Yeah, then I guess we could start going to your thesis work then. So the title is called Learning to Learn with Gradients. What kind of built up to this idea of, well, first, like what is meta learning and learning to learn? And then what like motivated you to start working on this specifically?
Yeah, so I'll first talk about the motivation. So in the beginning of my PhD, actually in my first year, we started working. Well, the first month I kind of helped out with a project as kind of just to get ramped up a little bit. But after that, in the first year of my PhD, I worked primarily on end-to-end deep learning for robotics. We completed that project in January of 2015, and that was actually a really exciting project. We were basically one of the first papers to show that you could train neural network end to end to basically produce a policy that maps from images that the robot sees as input to torques applied to the robot's joints and learn complex manipulation tasks like screwing a cap onto a bottle, um, like taking a toy hammer and putting it underneath it, like putting the claw of the toy hammer underneath a nail. And in a follow-up paper, we also showed that a similar technique could enable the robot to learn tasks like using a spatula to lift an object into a bowl. And all of this was learned with reinforcement learning techniques. And then
Mhm.
it was a really exciting result. The New York Times actually picked up on it as well. It got rejected from 2 conferences, RSS and NeurIPS, but it's now my second most cited paper. Um,
That's one thing I've learned in doing these interviews. It's a very frequent thing. It's like, an idea is good if it gets rejected a couple times first, or it's like
yeah,
a necessary condition almost.
yeah. So it got. I mean, in the robotics community was just very, very hesitant to kind of start accepting these deep learning based approaches.
Mhm.
Um, and we were really excited about it. But one thing that was dissatisfying about it was that while we were able to learn these tasks, each time the robot learned something new, it would be learning completely from scratch. And if you think about how like humans go about like learning motor skills, like we don't like have a blank slate, then learn one task, then have a blank slate and learn another task. And the way that we're training these robots was basically corresponded to like taking a baby, like a blank slate, and like teaching it how to use a spatula,
Mhm.
which is kind of ridiculous if you think about it that way. So that motivated our thinking around how we might build systems that can somehow leverage previous experience when learning new tasks. And ultimately, if we want robots to be broadly useful, we want them to do many different skills, many different tasks. We don't want them to just do one very narrow thing. If we want them to be useful in kind of everyday environments. So that was some of the motivation behind meta learning. And it seemed like there wasn't any existing algorithm that would allow you to take previous experience and use that to learn a new skill extremely quickly. There's things like fine tuning that may allow you to kind of gradually learn new things by leveraging previous experience, but we wanted something that would ultimately allow a robot to learn a new task with just kind of a few trials of that task, just how humans are able to like learn how to operate a coffee machine after a few attempts. So that was some of the motivation. And to your other question of like what is meta learning, first there's a lot of different definitions, but one definition that I'll give that we focused on a lot is assuming that you have a set of tasks or a set of data sets. Your goal is given that set of tasks, you want to be able to learn a new task from that same distribution of tasks very quickly at test time and with a very small amount of data. And what you do is you essentially train the model across that set of tasks such that when it sees a small amount of data from one of those tasks, it can quickly give you a model that does well at that task. And you do that for all of the tasks in your kind of meta training data set, such that when it sees a small data set for a new task, it can quickly adapt and produce a model that's effective at that task.
At the time, I guess, like you mentioned, some of the previous work. Like I think there were some papers even from the '90s doing some forms of meta learning. But I guess like this idea of doing it with gradients was maybe the new thing. So how did you kind of like rule out? Did you try out the existing approaches, or did you know that you needed something kind of new?
Yeah, so the existing approaches weren't, I think they're primarily either using kind of evolutionary methods. A lot of them were not really demonstrated on large scale problems. They're kind of demonstrated on very
Hmm.
toy problems. That made it kind of clear that maybe they wouldn't scale, at least as is, to the kinds of problems that we were interested in. And this is in like 2016, like late 2016 that we were working on this. And recently there had been a kind of a couple papers that had come out that had built approaches for few shot learning. One was the matching networks paper by Oriol Vinyals, that essentially trains a model to be able to match different images, and it's somewhat specific to classification problems. It's not readily applicable to regression problems, which is important for if you want to control a robot to in different ways. Any sort of continuous control problem. And then the other kinds of approaches were very black box, where you basically feed the data into a neural network, and you train that neural network to produce a model that will work for you. And that didn't. It seemed like that didn't necessarily leverage the structure of optimization algorithms in a way that in a way that would be kind of easy to train. for these models. And so the key idea behind the model agnostic meta learning algorithm, which is the first work that we did in like late 2016, early 2017, was to try to embed gradient descent inside the meta learner, and in particular try to learn initialization such that when you fine tune with a small number of gradient steps and a small number of data points, you generalize well to each of the tasks.
What's your intuition about the types of solutions that it finds? Because it's essentially saying that like you move in parameter space, and then you're kind of assuming that the parameter that you find is going to be nearby to solutions to different tasks. Is that kind of the intuition?
Yeah, so the initialization that it learns, I think that kind of intuitively it could very likely be nearby a lot of the solutions to different tasks. Um, it may also not necessarily be that nearby because it takes a few gradient steps, but those gradient steps may be quite large. It essentially
I
needs to
see.
be at initialization such that kind of gradient descent points in the right direction towards a very good solution. And so it could be somewhere that's actually kind of not nearby, but nearby in terms of like the optimization path. One other thing that's worth mentioning is when you have these over parameterized models, there isn't just a single solution, and there's kind of many good solutions for each of the tasks. There's a whole space of solutions, and so this actually gives a lot of flexibility to MAML-like algorithms because they don't need to kind of try to find a solution that's close to like the one optimum for each of the tasks. They just need to find a place that is close to a good solution for each of the tasks.
And then you did show these three different, or outlined, I guess, these like three different properties of the algorithms that you might want. So like expressive power, measurement, consistency, and handling ambiguity. You actually showed that just doing these gradient steps is kind of enough for certain models, at least. Like you have full expressive power, right?
Yeah. So what I mean by expressive power, and this was actually mostly just in response to a lot of people saying, well, like, is this meta learner like actually will it actually like be able to give you a wide range of learning procedures? It's very clear that if you just use an RNN as your learner, then that can kind of represent any possible learning procedure. It's extremely expressive, but when you're just learning the initialization, maybe this isn't sufficiently expressive. And so we had a theoretical paper that shows that if you have an extremely large neural network, then the initialization can basically allow you to represent any learning procedure with just a single gradient step. And the intuition behind this result is that in some ways you can just view MAML also as this as kind of a black box learner, except there's just this funny gradient operator in the middle of this computation graph. And this gradient operator, as long as that gradient operator doesn't lose information, as long as it's not like a lossy operator, then you're kind of in good shape. And so as long as you use a loss function, like an L2 loss function, for example, or a cross entropy loss function, such that the gradient doesn't like discard information about the label, then with a sufficiently large neural network, it can represent any learning procedure.
Yeah, I see. I really enjoyed that section about like the different properties. Yeah, so I guess like initially, or at least in the initial section of the thesis, the results are kind of on like regression and then these other tasks like omni-glot. Is that kind of how it went chronologically? Like, did you get this to work on those tasks and then it was still like an open problem whether this could be applied to the robotics tasks that you really maybe cared about?
Yeah. So we first did experiments on like regression, really simple regression tasks, simple image classification tasks, and also really simple reinforcement learning tasks, where like the tasks were just like to run backward or run forward. And we started with those just because it's a lot easier to iterate on those kinds of data sets than iterating on a real robot. And I really like doing a mix of work in kind of core machine learning with kind of very simpler experiments and also trying to apply that to real robots because this general idea of meta learning with kind of gradients in the inner loop isn't just applicable to robotics problems. It's applicable to a wide range of problems as well. And you can have greater impact when you also kind of develop really core machine learning ideas. And so after that, I was actually fairly confident that it should work well for some robotics problems. And there were two in particular that I think, most interested and excited about. One was the imitation learning setting, and the other was using it for model-based reinforcement learning, where you learn a dynamics model of the world, and then if different parts of the world have slightly different dynamics, like a legged robot running on different terrains, then you try to adapt your model very quickly with few-shot learning, and then plan with that adapted model. So these were two of the applications that we started looking at after the initial work.
Yeah, just on the point about the general machine learning, that I was kind of reflecting on this, and it does seem interesting that you were maybe motivated by these concrete tasks in robotics, but that allowed you to kind of find some more general solution that's now used for other things, like, I mean, even like image classification.
Yeah, absolutely. And I think that yeah, I think there are a lot of kind of real world problems that are shared by a wide range of applications. Like another problem that comes up in robotics is distribution shift. If kind of you train the robot at night and then during the day there's different lighting conditions, you want it to be able to be robust to those lighting conditions. And I think that's a problem that comes up in a wide range of other applications, and that's a problem that we've been studying a bit more recently.
Yeah, so I thought maybe we'd go to the few shot imitation learning section. I thought this was really interesting. And then if we have time, we can, of course, like discuss the other sections. Could you just describe the setup for this problem, maybe how you started working on it?
Yeah, so the motivation again is that if you want to train a robot, you typically train it from scratch. It requires a fair amount of data, and in imitation learning, the typically you need to collect demonstrations, which is like teleoperating a robot to do a certain task, and collecting a lot of demonstrations for every single task that you want the robot to do is very time consuming. And even just like typically when you do this, like what I mean by task here isn't even just like having a robot learn how to like use spatulas. It would be something like learning how to like kind of use a specific object in a specific context. And this means that the robot in kind of very typical reinforcement learning settings is really only trained to use a single object in a single environment for a single task. So in this work, kind of the way that we looked at it is we wanted to see if the robot could quickly adapt to a new task and learn to perform a new task with just a single demonstration. And in particular, in what we looked at with tasks here is we had different tasks correspond to different objects. So if the robot wanted to be able to place an object into a bowl, like a red bowl versus a blue plate versus some other container, or maybe the robot wanted to pick different objects up and put it into a certain container. Different objects would correspond to learning to interact with different objects.
I guess you have like these two forms of trajectories. So one is from the robot, and then one is from a human. And I guess the robot one is obtained, it said through teleoperation. So is that like someone's using a remote control on the robot?
Yeah, so we actually did the first work that we did on this. We didn't look at videos of humans. We just looked at kind of one-shot imitation from teleoperated demonstrations, and then kind of right after that, we looked at being able to imitate videos of people doing tasks. But I can focus on the second one. Um, but yeah, by teleoperation, what we did is we took a VR controller, a virtual reality controller, and you would basically move the controller in the way that you want the gripper to move, the robot's gripper to move, and then there's also a button to open and close the gripper. And this was used to operate the robot and provide demonstrations of different tasks. And then to provide videos of people, we would just basically show the robot what we want to do with our own hands, and the robot would watch and kind of collect the images from its camera.
Yeah, and then I guess you just mentioned it. So you started with first doing the one shot imitation learning from these robotic demonstrations, and then moving to, I guess, a more generic setting, which is like third person watching a human.
Yeah.
Yeah, and then here, I guess one of the innovations was this meta learned loss function. So this was another place, it was kind of like mind bending thinking about it at first. Could you just talk a bit about that idea and how, like, how it kind of became necessary in this problem?
Yeah, this is also something that was was hard to explain to people exactly how it works. It's a little bit different than kind of your standard machine learning setup. So the idea is that we wanted to be able to use a video of a human instead of a teleoperated demonstration to adapt, and we wanted to use the same kind of MAML algorithm where we're adapting with gradient descent. We just wanted to run fine tuning. And unfortunately, when you have a video of a human, you don't have labels. So when you have a teleoperated demonstration, you have both the image and you also have the action that the teleoperator took at every time step. So that gives you labeled data for training the policy. But when you only have videos of humans, you only have the images. You don't know what action the human hand took. And even if you did, that wouldn't necessarily be the best action that the robot should take. So what we did is, we said, okay, we don't have the actions. And so that means we can't evaluate the inner loop loss function that's going to give us gradients. So instead, what we did is, in addition to learning the initialization for fine tuning, we also learned this loss function, which is also a neural network that takes as input the activations and outputs a scalar value. And then we took the gradients of this loss function and used those gradients to update the parameters of the policy. And both the initialization and the parameters of the loss function are optimized with respect to the one-shot learning objective. And the outer loop loss uses the teleoperated demonstrations. So the inner loop uses the human demonstrations, the outer loop uses the teleoperated demonstrations.
Since then, have you seen anyone use this idea of meta learning a loss function in other contexts?
Yeah, so people have actually used it in a couple of different scenarios, and some of them, I don't even know if they kind of realize that we used it in the imitation learning work, because in general, with a paper, it's hard to convey more than one idea, and the one idea we wanted to convey in that paper was one-shot learning from videos of humans. Uh, so if you search for a keyword of like meta learning learned loss or something, you wouldn't necessarily find that paper. But anyway, people have used it. One place that people have used it is in reinforcement learning to essentially learn a critic that provides good gradients to a policy. Another place that people have used it is if when you're trying to learn a new task, you have both a labeled training set and an unlabeled test set, then you might want to use a learned loss function to actually leverage that unlabeled data in a way that allows you to adapt more effectively than if you only use the small labeled training set.
Yeah, because that's I guess the key thing is that you can avoid having the labels. So like the labels in the robotics case were the actions.
Yeah, exactly.
Yeah, yeah, I see. We were talking about how when you started the PhD, deep learning was barely being applied to robotics, and now at this point, like you're able to learn some tasks from a single video of a human. Uh, like, did you ever look back and think like, wow, this has come a long way, or was it kind of what you expected? Or maybe sometimes like when you're in the weeds working on a problem, maybe it like wasn't even impressive. I don't know.
Yeah, I did feel like we were able to make a lot of progress during my PhD, and I think we've still been able to make good progress on a kind of a wide range of problems. I think that whenever you kind of know all of the kind of intimate details of a method, then it doesn't seem quite as impressive. It's not. It's a little bit less magical because you know exactly how it works. I still feel like we have miles and miles to go in terms of the research goals that I'd love to accomplish, in terms of building kind of robots that can perform really a wide range of tasks in the real world. Uh, but I'm pretty happy with the progress we've been able to make.
I was thinking about this setting in terms of like the different levels of supervision. So you can think about like varying the amount of supervision you have, so like a whole data set down to one example, and then the type of supervision. So like you started with the robot trajectories and then just looking at a video of a human. Where do you kind of go next from there? Because it already seems fairly minimal. Like you're looking at a video from a third person.
Yeah, definitely. So while the kind of adaptation process is extremely minimal, the amount of data that's needed for the meta training process was quite a lot. And I'd love to move towards a setting where the data needed for meta training requires less human involvement. Ultimately, I think we need to move towards like data collection schemes that produce very large data sets. I feel like robotics is so far behind machine learning in many aspects because, like in robotics, for every single paper, we typically recollect a new data set for that paper. For the human imitation, we did actually reuse the data that we used for the imitating teleoperated demonstrations, but beyond that, like we're still like collecting new data sets for every single paper. And if you want to get to the ability to generalize at the level of models trained on ImageNet, for example, that would mean that we would need to collect ImageNet for every single paper that we want to write, which is just kind of completely unimaginable. So we need to move towards being able to leverage reusable data sets, being able to leverage unlabeled data sets, because that will allow us to collect more data and learn more from that data. So if we could do that same thing, but only requiring kind of unlabeled videos of people doing things and unlabeled videos of the robot doing things, I think that would be amazing. We do actually have some recent work where we've been looking at leveraging videos of humans as well. So that's one direction. Another direction is just generally broadening the space of tasks that we're considering. So we considered a set of pick and place tasks, a set of placing tasks, and a set of pushing tasks for that paper. But ultimately, we'd want a robot to be able to perform any manipulation task and be able to kind of learn how to pour water or fold a t-shirt or stir soup or something. And moving towards that much broader range of tasks is something that has still been elusive to our methods.
Yeah, so I guess you're saying that like the meta learning does get you something in the sense that you can adapt to a new task, but you're still constructing. You still need a task distribution, and to build that task distribution, you need to do some upfront work. Is that kind of the general idea?
Yeah, exactly. And if we could kind of get rid of that upfront work and instead leverage some unlabeled data or be able to incrementally construct these data sets and reuse data sets repeatedly, I think that would move us in the right direction. The other thing that we've also been exploring recently is being able to reuse data sets across labs. So it's very common to share data sets like ImageNet across labs in machine learning and in computer vision. But when each lab has their own robot, their own control, their own action space, their own environment, it makes it harder to share data across labs. But if we can actually collect data and share that across labs, then we may be able to get to the point where we can, it becomes easier to kind of have a data set that has lots of tasks of robots doing things and leveraging that for a meta learning system. So we've been starting to look at this, but it's there's obviously a lot of challenges with transferring across robot platforms.
So it seems like maybe what you're saying is that like robotics still needs to have the kind of ImageNet or GPT-2 type moment where you kind of figure out how to do some kind of large pre-training phase on some type of data with some type of algorithm, and then potentially do, now that you have some pre-trained model, then do meta learning after that. Is that kind of the high level picture you're seeing for the future, or?
Something like that. I think that is also not quite that simple either, because even if we had a great pre-trained network, it's not also not clear how you fine tune. Running reinforcement learning on a real robot in the real world is still a process that requires a lot of careful engineering. You need to figure out, well, if the robot, well, especially, it depends on how long it's going to take, but if it's going to take like an hour or two, then you still need a human there often to reset the environment back to some initial state, to provide some reward information, to kind of figure out where the camera should be located, like what's a good viewpoint, what sort of sensor should you use? Should you use two cameras to get 3D information? There's all sorts of kind of careful engineering choices that go into it, and reinforcement learning algorithms are also quite brittle. So both to kind of some of these choices and also to hyperparameters. So there's a lot of work to do, I guess. I'm excited about methods that can leverage large data sets, though, as a means towards towards building better kind of pre-trained representations, towards learning more general behaviors, and towards kind of ultimately generalizing to more environments and more objects.
I did just want to touch on this one other section about the few shot goal inference or few shot intent inference. I thought this was a really cool idea as well. That I was thinking of all these different applications it could have in like natural language processing, where we use human evaluation for a lot of things, and you could imagine that like for different NLP tasks, human evaluators might use some kind of common features when they're assigning a score to how good a model output is.
Yeah, so this is maybe something that NLP and robotics share in common is that like evaluating a policy is hard. It's not necessarily trivial, and it often requires some sort of human involvement. And also providing reward functions, as I mentioned before, is also kind of difficult as well. And so our idea here is that we wanted to be able to quickly learn a classifier that would tell the robot whether it succeeded at a task. And typically, of course, if you want to learn a classifier, you need to collect a fair amount of data, especially if it's an image classifier. So instead, we wanted to basically provide a few examples. One thing that was a bit different is that, well, if you want to learn a classifier for a task, it'd be nice just to provide a few examples of success and not have to try to also cover the space of failures. So we were looking at few shot learning, but few shot learning only from positive examples and not including any negative examples of failure. So what we did is we collected for the meta training process. We collected both positives and negatives of different kinds of tasks, like we were looking at kind of like relative object placement tasks where you want to put the fork on the right of a plate, or you wanted to put a kind of a pencil kind of below or behind a piece of paper or something like that. We collected a bunch of these images from these different tasks, both positive examples and negative examples, and then did a kind of meta-learning algorithm such that when it ran gradient descent with respect to just a few positive examples of the task, about 5, I think, then it could learn a classifier that told you success or failure for that task. And then once we got the success classifier, we then actually took a planning algorithm and ran the planner with respect to that success classifier and showed that the robot could learn these different object arrangement tasks just from a few examples of success.
Yeah, so it was like a different spin on, I guess before people had done like this inverse reinforcement learning to learn a reward function. Instead, you're learning these success classifiers. Yeah, that was really interesting.
Yeah, and we also actually had a paper on kind of integrating meta learning into an inverse reinforcement learning procedure as well, and showed that you could try to learn a reward function with inverse RL with a few examples. Learning success classifiers is a little bit easier than learning reward functions with inverse RL. Inverse RL is like a whole nother can of worms that I also worked on a fair amount during my PhD. But yeah, in general, it seems like that's also an area that I'm excited about because when you think about when humans look at someone else doing something, if you're trying to tell the intent of that person and you're trying to understand their intent from just like one example or a few examples, if you're starting from scratch, there's no way that you would be able to understand what they're trying to do. They may be trying to reach towards a certain position, reach towards an object, reach away from something. It's a inherently underdefined problem. And it seems like a very natural fit for meta learning because meta learning gives you a mechanism to encode prior information. And if you have a prior over what the human is trying to do and what sort of tasks are interesting and meaningful, then you should be able to much more effectively infer their intent. So that's kind of an area where I think that actually meta learning or some form of learning priors makes a lot of sense.
One major thing that people have been talking about, I guess, is this GPT-3. And I think it is relevant to this discussion because it seems like it has this behavior where you can now give it a few examples in its context, and it quickly learns the task that you encoded in the context. So it almost seems like it's acquired. Yeah, it somehow learned to learn just through this language modeling pre-training. I just want to get your opinion on like how you view this result.
Yeah, so I think that in many aspects, I think that the result is incredible. I was quite excited to see some of those examples. And the method in many ways can sort of be viewed as what I typically call a black box meta learning method, where you basically just feed in some data into a black box neural network and then tell it to produce stuff. But also can be obviously be interpreted not as a meta learning algorithm.
Yeah, yeah.
I like that it has a mechanism to leverage what language models in general have mechanisms to leverage very large amounts of data that are just kind of readily available. And I think that that's part of what makes them so powerful. I also think that the the failure cases are quite illuminating and makes it
Mhm.
pretty clear, at least to me, that we have a lot of work to do on the machine learning front, beyond just feeding a lot of data into these systems to build systems that are robust and maybe have a bit more broader understanding of like the world.
Do you think that maybe though this suggests that it's worth trying these sort of like recurrent based meta learning methods on just massive amounts of data, and that they might be more promising now? Because I think like one thing you showed in your thesis is that the recurrent methods for doing meta learning weren't working as well, but maybe this suggests that they just need massive amounts of data, or maybe we don't have the data is the thing.
Yeah, so I think that there are kind of pros and cons to both. I think that some of these like recurrent network-based approaches, it's pretty easy for them to adapt to a wide range of data in a way that gradient descent essentially builds an inductive bias into the learner to kind of look like an optimization. And if you want it to do something that's a bit different than that, then I think that a recurrent network is more natural. Um, in some ways, I think that gradient descent may be slightly more robust to things that are a little bit out of distribution, because if you run gradient descent on a data set that you're given at test time, you're at least know that it will like descend on some objective and improve, even if the data that you give it is far from the task that you fed into it. Whereas if you kind of feed in some out of distribution data to an RNN, like you really have no idea what it is going to give you. Then again, if you have this massive data distribution, then that's not necessarily a problem to be concerned about. So from that standpoint, I think that kind of as the data sets get larger, the RNN and kind of black box based methods can make a lot of sense in meta learning contexts.
Hmm. I see. Yeah, I guess like since the PhD, now you're a professor at Stanford. What are some things that you're currently excited about? And I guess, well, I think the answer is yes, but are you still working on meta learning?
Yeah, so two things that I'm excited about right now. One is on the robotics side. I think that we need to figure out how to leverage massive data sets. I think we're taking steps in the right direction, but I think we haven't quite figured that out yet. And that will hopefully get robotics more up to speed with the rest of machine learning. And then on the machine learning side, I think we really need to figure out better techniques for handling distribution shift. I think that we figured out how to leverage large data sets, but we haven't figured out how to go beyond those data sets or how to learn when those data sets are heavily imbalanced or have very long tail distributions. So that's a problem that I'm excited about and actively working on the machine learning side. I am still working a lot on meta learning, and we've actually been looking at how meta learning can allow you to adapt to distribution shift. A lot of ideas for handling distribution shift are typically trying to train a model to be robust to that sort of distribution shift. But if you have a little bit of data at test time, unlabeled data at test time, then you might be able to use that to infer what part of the distribution that you're in, and then adapt your model to that distribution shift, and hopefully do better than a
Hmm.
model that's trying to do kind of equally well on everything.
Yeah.
Yeah, and then I've been teaching a course on meta learning. So I taught it last fall, and all the lecture videos are online, and I'm teaching it again.
Oh, nice. So it's yeah starting up again, and those
Yeah,
will be online as well.
yeah, they'll be online after the quarter. It takes a while to process them to make them publicly available because they need to cut out student faces for privacy reasons and also caption all the videos for disability reasons. So it takes a little while, but they'll all eventually be available after the quarter ends.
Just looking back on like your PhD and your research career so far, do you have any like advice that comes to mind, maybe for someone starting a PhD or just getting into the field?
Yeah, so one thing that worked really well for me was to try to be a little bit picky about the problems that I worked on and the methods that I worked on. I really tried to work on the problems that I felt were some of the most important problems to be working on and the problems that I was the most excited about. But of course, also the problems that I felt like we had a good idea for how to make progress on. You don't want to just pick a really hard, exciting problem, but have no idea how to make progress on it. So it's important to have both of those. But I think it's especially important to make sure that you're excited about what you're working on. It it makes it a lot easier to work hard on something. I felt like during my PhD, I was really it was less work and more play. In many ways, I felt like I was just learning about all sorts of things, and I felt like I was just playing all the time rather than working all the time. And and it also makes it easier to solve problems if you're kind of continuously mystified by something and then you sleep on it and come up with a solution as you're when you wake up or something. That I feel like that's sort of the best research gets done if you're really excited about it.